Welcome to Ask and Learn.
Hello students, a long thin non-conducting plastic rod is bent into a circular loop that has a radius. So this has a radius A, right? Loop has a radius of A. Between the ends of the rod, a short gap of length L, right? So L is there. There is a gap here between the ends of the rod. So this is the rod and there is a gap here. So L is very much less than A. So it's too small. A positive charge is evenly distributed on the loop, right? So the charge is equal to Q. What is the direction of the electric field at the center of the loop? Okay, the direction of the electric field at the center of the loop will be perpendicular to the plane of the loop, right? So to understand why the electric field is directed in perpendicular, we can consider the principle of electrostatics. So according to Coulomb's law, the charges exert a force on each other. So here there is two charges, like charge, there is a charge here but there is a separation. So the force is equal to Q by R square times K in the R cap direction, in the radial direction. So when we have a circular loop with uniform charge distributions, the electric field produced by each element of the charge on the loop add at the center of the loop. So the electric field vector contributed to each charge element point in different directions along the circumference. So this will, let's draw a vector like this. Okay, so it has to start from here. So from different end, this electric field goes through the center like this. Okay. However, due to symmetry, the magnitudes of the electric field vectors cancel out in all directions except the perpendicular direction. So everywhere it cancels, but in the perpendicular direction of this loop, this doesn't cancel. So the contributions from opposite sides of the loops cancel each other out in horizontal directions, resulting in a net electric field only in the vertical direction. So therefore, at the center of the loop, the electric field is perpendicular to the plane of the loop. This is perpendicular to the plane, that is the electric field. Okay, this is a solution for the first part. Now, this is the first part. Now coming to the third part. What is the magnitude of electric field at the center of the loop? What is the magnitude? So electric field, to determine the magnitude, we can use Gauss's law. So in this case, we can consider cylindrical Gaussian surface, a cylindrical Gaussian surface as it passes through the center of the loop, right? So since the charge is evenly distributed in the loop, the total charge enclosed by the Gaussian surface is Q. So the electric flux phi is equal to electric field times area. That is equal to electric field times 2 pi A times the length 2 pi A. 2 pi A will be the area, right? So that will be not 2 pi A, but it is going to be pi r square. So let's assume this has a height of h. So 2 pi A times h will be the area. So flux phi will be equal to Q by epsilon 0 according to Gauss's law. So electric field will be equal to 2 pi A times h times that is equal to Q by epsilon 0. So we can simplify this. So electric field is equal to Q by, so not this, so this times this is equal to that. So Q by 2 pi A h epsilon 0, right? So here this is the this is the what this is the electric field, but here h we can assume it to be equal to this infinitely similarly small. So let's assume it to be equal to infinitesimally small. So E will be equal to Q by 2 pi A. Let's say A is very much higher than H. Okay, so 2 pi A times epsilon 0. That is the electric field at the center of the loop given by this equation. Okay, so this is a solution. I hope you find the solution useful. Thank you.